I'm sharing my screen. So we left with two more topics. That is RTL code for asynchronous counters and RTL code for frequency divided circuit. That frequency divided circuit we'll see tomorrow. So today we'll focus on the RTL code for asynchronous counters. Okay. So asynchronous counters are like so the common clock is not given. The output of one flip flop is act as a clock for the next flip flop. Okay. So first of all, I will show you. I will tell you the design. How to design this asynchronous counter. Asynchronous counter. Okay. Asynchronous up counter. Okay. So if you see, yeah, asynchronous up counter. Asynchronous up counter. So asynchronous up counter. If you see. So there are steps are there. First, steps are there. So step one. So step one is choose the type of flip flop. Okay. So choose the type of flip flop and number of flip flop. So asynchronous 3-bit counter I am designing. So 3-bit counter means choose three flip flops. Okay, three T flip flops. Okay, and step two. So step two, T flip flop must be in toggle mode. Okay, whatever the T flip flop you are using, T flip flop must be in toggle mode. Toggle mode. Okay, and next step three. So always clock is applied to the LSB of the flip flop. Okay, so clock applied to LSB of my flip flop. LSB of the flip flop. Okay, LSB of the flip flop. Okay, that is T naught. Okay, and step four, output of T naught. So that means output of T naught, output of T naught is applied as a clock to the a clock signal to the T1 flip flop and so on. Okay, so output of T naught is applied as a clock. Okay, as a clock signal for T1 T1 flip flop T1 flip flop and so on. Okay, and so on. So that means here, if you want to design this asynchronous counter, so how many 3-bit counter? Three flip flops are there. So three T flip flops are there. You are designing with three flip flops, and next T naught, Q naught, T1, Q1, and T2 and Q2. Okay. So these all flip flops will be in which mode means toggle state. So this will be given to toggle state. Okay, so that is one. Okay, you know the T flip flop truth table. So T and Qn plus one. So when T equal to 0, this will be in the memory state. T equal to 1, this will be in the toggle state Qn bar. Okay, and I am giving negate of clock. Okay, so always clock is applied to this negate of flip flop, LSB of the flip flop. Okay, this is LSB of the flip flop. Okay, so T naught is LSB of the flip flop, and Q naught is acting as a clock for the next flip flop, negate of flip flop. Okay, and Q1 is acting as a clock for the negate of flip flop. Okay, so just if you want to analyze, so here I am writing like clock next q naught. Okay, let us take this is q2. Q2 is msb of the flip flop, q2, q1 and q naught. Okay, q naught is lsb of the flip flop. Okay, so that means you are applying clock 0. Okay, when you are applying clock 0, initially all the flip flops will be what so all the flip flops will be zeros only. So all the flip flops will be initial state. Initial state means zeros only. Okay. So when you are not applying any clock, all the flip flops will be zero only. When you are applying first clock, okay. So what happens? So here this will always this will trigger. This will trigger from 0 to 1. Okay. So as this is triggering from 0 to 1, what happens? This is negage. Negage means when it will trigger. So when it is going from 1 to 0 only, it will trigger. Okay. So passage means, so this is passage of clock. Negage means when it is coming from 1 to 0. So this is negage. Okay. So this will be 0 to 1 means passage only. It will be in the same state only. Okay. Again, no transition. So no transition means, so this will be in the same state only. So at first clock, the output will be what? Output will be uh, so 0 0 0 0 0 1. Okay. And next at second clock, what happens? Always this will trigger. So it will trigger from 1 to 0. So 1 to 0 means negate. This will toggle. Okay. 0 to 1 means there is no so passage of clock. So that means it will be in the previous state. Okay. So this will be what? 0 1 0. Okay. 0 1 0. Okay. And at fourth clock pulse, third clock pulse, you will see. At third clock pulse, again this will toggle 0 to 1. Okay. 0 to 1. 0 to 1 means passage only. It will be in the previous state only. So again no transition, it will be previous state only. So that is 0 1 1. Okay. And at the fourth clock pulse, what happens? At the fourth clock pulse, again it will toggle. So 1 to 0. So 1 to 0 means negate. Negate means this will trigger. So this will trigger. So this will toggle from 1 to 0. So 1 to 0 means negate. Negate means what? It will toggle. So at fourth clock pulse, you will get 1 0 0. Okay. And next at the fifth clock pulse, we will see. At fifth clock pulse, again it will toggle from 0 to 1. 0 to 1 means passage. It will be in previous state only. No transition. It will be previous state only. So that is 1 0 1. Okay. At sixth clock pulse, what happens? At sixth clock pulse, again it will toggle. So 1 to 0. So 1 to 0 means it will toggle. 0 to 1 means passage. So passage means no transition. This is 1. Okay. So 1 1 0. Okay. Like this we are getting. At seventh clock pulse, again it will toggle. Okay. 0 to 1. 0 to 1 means passage. Passage means it will be in the same state only. There is no transition. Again it will be in the same state only. So that is 1 1 1. Okay. At seventh, at eighth clock pulse, it will come to the initial state. See here. So it will toggle from 1 to 0. Negate. So negate means this will toggle. So again this will toggle to 1 to 0. This is negate. Again this will toggle from 1 to 0. So it will come to the initial state 0 0 0. Okay. So if you want to draw the state diagram, so initial state is what? 0 0 0. Okay. If you apply first clock pulse, it will come to the next state, that is 0 0 1. Again second clock pulse you are applying, next it will come to 0 1 0. Okay. Third clock pulse, it will come to 0 1 1. And at fourth clock pulse, it will come to 1 0 0. At fifth clock pulse, it will come to 1 0 1. At sixth clock pulse, it will come to 1 1 0. Okay. At seventh clock pulse, it will come to, okay, third clock pulse, fourth clock pulse, fifth clock pulse, sixth clock pulse, and seventh clock pulse. It will come to 1 1 1. At eighth clock pulse, it will come to the initial state. Okay. So this one we can call as mod 8 counter or 3-bit up counter. 3-bit up counter. Okay. Is this operation is fine? Do you understood? Shall I move forward? For this, I am going to write the Verilog code. Okay. Yeah. So here you see. So I wrote the Verilog code for this. So go to so, yeah. So sequential circuits, flip flop, asynchronous counters. Okay, asynchronous counters. 3-bit up counter. That is 3-bit up counter. Okay, 3-bit up counter. So here, if you see, so it will start with module ripple counter and asynchronous counter both are same only. So other name for asynchronous counter is a ripple counter. So module ripple underscore counter 3-bit. I need to declare input clock, input reset, output 2 down to 0 Q. Okay. So as this is 3-bit, I am using a vector called 2 down to 0. Okay. And I need to declare the internal resistors. Okay. Internal registers, those are Q1, Q0, Q2. Okay. Internal registers I need to declare. Okay. Internal registers of each flip flop. Okay. So stage 0. So stage 0, what happens? Always at the rate negate of clock. Okay, every flip flop will be toggled during the negate of clock. No, every flip flop will toggle during the negate of. So I given through the bubble. Okay, so this is negate of clock. So during the negate of clock or passage of reset, begin if reset equal to 1, q naught I am making as 0, else say q naught equal to naught of q. Okay, so this is stage 0. Okay, and that is for flip flop 0. Okay, flip flop 0, so that is q0. Okay, so q0, so this will toggle, always this will toggle. And stage 1, if you see, stage 1 toggles are negate of q naught, so that will toggle when q naught toggle from 1 to 0. Okay, q1 toggles from 1 to 0. So that means what I can write, always at the rate negate of q naught or passage of reset, begin if reset. Okay, if reset q1 equal to what, 1 tick binary 0. I need to get the output q1, no? So 1 tick binary 0, else q1 equal to toggle. That means q1 equal to naught of q1. Okay, this is stage 1. Okay, so that is this you can consider as stage 0, and this you can consider as stage 1, and this you can consider stage 2. Okay, so stage 1 is completed. And next, coming to the stage 2. Stage 2, when it will toggle, that is third flip flop, when it will toggles on the negative edge of q1. Okay, when you are getting at the negative edge of q1, then it will toggle. Okay, so always at the rate negative edge of q1 and passage of reset, begin if reset. Okay, if reset, so q2 is will be initialized to 0. Okay, if reset equal to 1, else q2 equal to naught of q2. Okay, it will toggle. Okay, and combine the, so end means what, till here procedure blocks is ended. Okay, and at last what you need to do, you need to use a continuous assignment statement, assign. And I'm using a concatenation operator, q equal to what, q2, q1 and q naught. Okay, so you need to get like this only, no? So in the here also, in the table also I wrote q2, q1 and q naught. So I'm combining, so q equal to q2, q1 and q naught and end module. Okay, so this is my RTL code for asynchronous counter. Okay, is it fine? Did you understood? Shall I move forward? Based on this diagram only, I wrote for 3-bit up counter. Okay, and coming to the ripple count test bench. Coming to the test bench, here you see, so module TB ripple counter. So whatever the clock and the set is there, I'm declaring with reg data type, and q I'm declaring with y data type. Okay, and I'm instantiating my design in the test bench. Okay, how I'm instantiating, design name followed by instance name, and this is connection by name. Okay, and after this, so whatever the variables outside the bracket are design input and outputs, and whatever the variables inside the bracket are test bench variables. Okay, and next you need to generate the clock, always hashtag clock equal to not of clock, initial begin. So initialize, that means initialize the clock equal to 0. I'm applying the reset. Okay, I'm applying the reset, that is 1. Okay, and after 15 time minutes I'm deasserting the reset, I'm releasing the reset. Okay, and I need to check for 0 to 7 cycles. No, that will be around 80 nanoseconds. So that means I need to run for 100 time units. Okay, 100, I need to run for 100 nanoseconds, and dollar finish, simulation finished, dollar finish end. And I want to see the outputs in the TCL console also. So for this I am writing dollar monitor. Is there any change in the variable, then it will display. So time equal to time also, if I want to check, time equal to percentage, the format specifier is 0t, and reset is percentage b, and count is concatenation, that is q2, q1 and q0 percentage b, comma, and dollar time. So time we are represented in the data types, we already see dollar time reset q comma q. Okay, so that means I want to display in binary as well as decimal, that's why I am writing as q comma q and end module. Okay, so for sequential circuits, the test bench is same only. Five steps you need to follow. Initialize the edge variables and instantiating. You are designing the test bench, generate the clock, and initialize the edge variables. Here you declare the edge variable, declare the internal variables, and giving the stimulus. Okay. So that are the only five steps we need to follow. Okay. Is the test bench and design is fine? Shall I move forward? Anyone give response so that I will move forward. Yeah, yeah. Thank you. So just I want to show in Vivado how we are getting. So just file project, new project, next, and project name is asynchronous counters. Okay, I am giving the project name is as asynchronous counters. Asynchronous counters. Okay. Uh, so again, go to the location. So here my ASIC uh, RTL, no, RTL, where I created this RTL G11 weekend batch. RTL codes using Xilinx Vivado. Next, next. So create the file name. So it may be the module name also. We can give module name also. Just to copy this and save. Choose the location. Okay. I created asynchronous counters. No, this asynchronous counter. Select. Okay. Next. And this is optional only. Next, next, and finish. And module name is also same. So just I'm copying this code, copy, and next save. Okay, and next test bench. So test bench, copy this module name and go to the simulation. Add, add the simulation source. Create and choose the location. Asynchronous counter. Select. Okay, finish. Okay, yes. So here my simulation file tb underscore ripple counter is created. Just select all, copy, and next here you paste. Okay, save. One second. Yeah, one more module is there now. Just I will delete. Save. My design is instantiated in the test bench. So my instance name is UUT and my net design name is ripple counter. Okay, both are same only. Ripple counter or say asynchronous counter, both are same only. So run simulation, run behavioral simulation. Run simulation, run behavioral simulation. So here you can see in the TCL console also. See here. That means when reset equal to 1, all the Q2, Q1, Q0 are 0 only. Okay. So when reset equal to 0 only, it will go into the functional mode. Okay. So that means here you see during this time, it is counting from where to where 0 to 7. After that, it is coming to the initial state, that is 0 again 1 2. Okay, you can see in the TCL console, or you can see here also, just fit to page, see here. So that means when reset equal to 0, we are getting like we are getting 0 only. Okay, and during the negate only that counting starts. Okay, during the negate of clock only the counting starts. It will counting from 0, 1, 2, 3, 4, 5, 6, 7. After 7 it is coming to again 0, 1, 2. Okay, so if you want to see in the binary also, so radix and binary. Okay, so it will start from the initial state 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Again it is coming to the initial state 0, 0, 0, 0, 0, 1 and 0, 1, 0. Like this we will get. Is it fine? The simulation is fine. Any doubts or queries? Okay. So this is about the up counter, and so we'll discuss up counter, down counter, and decade counter. Okay. Suppose so for RTL code, prerequisites are digital. Okay, I want to know about how about digital, means I am telling both digital and RTL concepts. Have you aware of these digital concepts or not? Have you aware or not? I want to check. Can anyone respond? Unmute yourself and respond. So yeah, okay. Next, asynchronous down counter, asynchronous down counter. Okay, so asynchronous down counter means so here three flip flops are there. So three flip flops. So three flip flops T naught, Q naught, T1, Q1, T2, and Q2. Okay. So common clock this T1 and T naught is given to the toggle state. Okay, this is given to 1. Okay, again always negate of clock is applied to the first flip flop, and next Q naught bar, Q naught dash is acting as a clock for the next flip flop. Okay, so Q naught dash is acting as a clock for the next flip flop, and the next Q1 dash is acting as a clock for the next flip flop. So this is down counter. Okay. So how to analyze this? So here I am writing, that is clock, and next Q2. Q2 is MSB bit. Okay. Q1 and Q naught. Okay. So when clock equal to 0, so all the flip flops will be initial state only. Okay. Just 1 second. 1 second. 1 minute. హలో, ఇప్పుడు కొంచెం పర్లేదు, ఆ టాబ్లెట్ వేసిన తగ్గింది తగ్గింది, అవుతుంది అవుతుంది, ఇకపోతుంది బాగుంది. చేస్తున్నా. ఓకే, అయిపోయింది, ఇప్పుడు బయలుదేరినా. సరే సరే సరే, ఓకే. So here, yeah, sorry for this interruption. Okay, so here initially all the flip flops will be 0 only. Okay, all the flip flops will be 0 only, and if you are applying first clock pulse, this is 1, and initially this is 1. Okay, this is 1, and this is 1. So this will come to 0. Okay, so 1 to 0 means what? Negative transition. So that means so initially, 1 second, Q not Q2. Yeah. So negative transition means so if it is 0, it becomes 1. No, 0 to 1 means it will toggle. So that means it will toggle. So that means this will toggle to 1, and 1 to 0 it will toggle to 1. So first clock pulse it is 1 1 1. Okay, it will start from 1 1 1, and second clock pulse what happens? This is 1 1 1. So so this becomes what? So this will toggle. This becomes 0. This becomes 1. Okay. So 0 to 1 means no transition. No transition means this will be 1 only. So this is 1 means this is 0. So here also no transition. This is 1, this is 0. Second transition it comes to 1 1 0. Okay. A third transition. Okay. A third clock what happens? It will toggle from 0 to 1. Again this will toggle from 1 to 0. Now transition is happening 1 to 0. So negate of clock. This Q naught dash I need to check. Okay. So it will toggle. So it will toggle to 0. As this is toggle to 0, 0 to 1. This is passage of clock. So passage of clock means it will be stay in the same state, and this is 0. Okay. So at third clock pulse it becomes 1 0 1. Okay. At fourth clock pulse, so it will toggle to 0. Okay. Again it will as this is toggle to 0, it toggles to 1. Okay. 0 to 1 means it will be in the same state, and this is 1, no transition, it will be in the same state. Okay. Fourth clock pulse you will get 1 0 0. Okay. At fifth clock pulse what happens? At fifth clock pulse again it will toggle from 0 to 1. So as this toggle from 0 to 1, it will toggle from 1 to 0, negative transition. So negative transition means it will toggle. Okay. Again 0 to 1, this becomes 0. Okay. Again 1 to 0 means again it will toggle to 0. Okay. So you are getting 0 1 1. At sixth clock pulse what happens? Again it will toggle to 1 to 0. Again here it will toggle from 0 to 1. 0 to 1 means passage, no transition. This is 0. 1 to 0 means it will toggle. It will be in the same state only. So 1 to 0 and this is 0 to 1. It will be in the same state only. So in sixth clock pulse it becomes 0 1 0. Okay. At seventh clock pulse what happens? At seventh clock pulse it will toggle from 0 to 1, and here it will toggle from 1 to 0. So it will toggle so it will toggle from 0 to 1 and 1 to 0. So again it will toggle. So this will toggle. So that means 0 0 1. Okay. At eighth clock pulse 1 to 0, 0 to 1. So it will be in the same state. 1 to 0, 0 to 1 means it will be 1 second. 1 to 0, it becomes 0. So at eighth clock pulse it becomes all zeros. Okay. All will be toggle. Okay. 0 0 0 at okay, it will come to the initial state. Okay. At eighth clock pulse it will come to the initial state. Okay. So like this we can analyze the asynchronous counter. So you see this code as a asynchronous down counter. Asynchronous down counter. So this is the code for asynchronous down counter. So module asynchronous down counter, input clock, input reset, output 2 down to 0 Q, and I am declaring internal resistor, that is Q0, Q1 and Q2. So stage 0. Stage 0 is what? That is this is stage 0. This is stage 0. Stage 0, stage 1, stage 1 and stage 2. Based on this I am writing the code. Okay. Uh, this one or will go. This one I will close. See here, always at the rate negate of clock or passage of reset begin if reset. So Q naught initialized to 0, else Q naught should toggle. Always LSB of the flip flop will toggle. Okay. Stage 1. Stage 1 toggles on what? On negative edge of Q naught complement. That is negative edge of Q naught dash. Okay. So always at the rate what? So that means if it is a q negate, that means q naught dash is negate, q naught becomes passage, no? So that means I can write always at the rate passage of q naught or passage of reset I can write. So if reset q1 equal to 0 and q1 equal to naught of q1. Okay. So that means stage 2 also toggles on negate of q1 complement. So note negate of complement of Q1 is equivalent to what? Passage of Q1. Okay. So that means always at the rate passage of Q1 or passage of reset. Here you can write that also. So passage of begin if reset Q2 is what? I am initializing to 0, else Q2 equal to naught of Q2, and you need to concatenate Q2, Q1 and Q0. Okay. This is my design, and coming to the test bench. So this is my test bench. So module TB synchronous counter. I need to declare the internal variables reg clock, reg reset, wire 2 down to 0 Q. I need to instantiate my design in the test bench. Design name followed by instance name, and I need to generate the clock. Okay, hash 5 clock equal to not of clock, and initial begin clock equal to 0. I'm applying the reset. After 15 time minutes, I'm deasserting the reset. I want to observe for 160 time minutes. I'm using two observations. That's why I'm giving the delay as 160 nanoseconds. And after that, I want to see in the TCL console, I need to use dollar monitor. If there any change in this variable, then it will display. Okay. So I want to see in the Vivado, just asynchronous down counter. No. So if you see asynchronous down counter, so copy, and this is design source. Add the design source. Choose the location. Asynchronous counter. Select OK. Finish. OK. Yes. Asynchronous down counter. And next, select all. This is my design. Copy. And here you paste. Save. And next, coming to this test bench. Copy. Again, you go to simulation. Add simulation source. Create simulation source. Create. Choose the location. Asynchronous counter. Select. OK. Finish. OK. Yes. TB asynchronous down counter. And select all. Copy. And here you paste. And save. So my design is instantiated in the test bench with the instance name UUT and asynchronous down counter. Okay. So right click and set as top module. Run simulation. Run behavioral simulation. So you can see in the TCL console also. See here. So it will start from where when reset equal to 1, the Q2 down to 0 it will be 0 only. Okay. So it will start from 0. When reset equal to 0, it will go to the functional mode. 76543210. Again 76543210. Okay. So you can see in the waveform also. Just fit to page. See here. When reset is applied, it will be in 0 only. So during the negate of clock, it will start counting. Okay. 76543210. Again, it will start from the initial state. 7. So initial state 0. Okay. It will come to the initial state. Again 76543210. Again, it will come to the initial state. So if you want to see in the binary, radix binary. So you can see like 0 0 0. It will start from 1 1 1 and 1 1 0 1 0 1 1 0 0 0 1 1 0 1 0 0 0 1 and 0 0 0. Again it will start from 1 1 like this. Okay. So this is about the down counter. Is it fine? Any doubts or queries related to down counter? Shall I move forward? Okay. Yeah. Thank you for confirmation. Okay. Next we'll discuss counter design of Mod 6 counter. Okay. So design of Mod 6 counter. So there are steps are there. Okay. So we'll see design of Mod 6 counter. So if you see the design of Mod 6 counter, so how it will count? So what is the count values? That is, it will count from 0, 1, 2, 3, 4, 5. Again, it will come to the initial state. Okay. So 0 and 1. So here, what states are skipping? It will skip the count. So what states? States 6 and 7. Okay. So there are steps are there. First step 1, you need to like design. So n is what less than or equal to this formula I told you. Okay, n is less than or equal to 2 power n. So n is less than or equal to what? So that is 6. 6 is less than or equal to 2 power n means. So n what I can take to satisfy this condition. If I place 2 cube, 6 is less than or equal to 2 cube means 8. Okay, this condition will satisfy. So how many minimum flip flops are required? So minimum 3 flip flops are required to design mod 6 counter. Okay, so this is the formula to check the number of flip flops. N is less than or equal to 2 power n. Okay, and step 2. Okay, step 2, you need to design mod 8 counter which is nearest to full modulus of a counter. Okay, design mod 8 counter, counter, mod 8 counter, which is nearest to, which is nearest to full modulus of a counter, full modulus of a counter. Okay, of a counter. And step 3, first you need to design the mod 8 counter. Okay, so as counter reaches, okay, counter output, whatever the counter output reaches double 1 0. Okay, double 1 0. So we need to activate the reset pin. Activate the reset pin. Okay, you need to activate the reset pin. Okay, reset pin using combinational logic. So I need to develop a combinational logic such a way that when it is coming to 1 1 0, so it should reset the output of all the flip flops. Okay, so how you can design the combinational logic? Suppose here you have so let us take QC, QB and QA. Okay, so here I am writing QC, QB and QA. Okay, I am developing the reset logic. Okay, so reset logic. So 0 0 0. So three inputs are there. So it will count. First you need to develop the mm, uh, mod 8 up counter. Okay, 3-bit up counter. 0 1 1 1 0 0 1 0 1 1 1 0 and 1 1 1. Okay, so that means here till I am designing active low reset. So that means till 5 it will be in the functional mode only. So that means reset logic should be high only, and when it will come to 6, reset logic becomes 0. Okay, okay. So if I see this one, that means so what is the reset logic? Reset logic is summation of m of from where to where it is 1, from 0 to 0 to 5 it will be 1. Okay, 0 to 5 it will be 1. So I am drawing the k map. So here if you see QC, QB and QA. Okay, 0 1 0 0 0 1 1 0 1 1 0 1 2 3, next to 4 5 6 7. Okay, so 1 0 1 2 3 4 again 5. Okay, so this is one quad and this is one quad. Okay, this is one quad. So if you see so R equal to what? QC bar plus QB bar. Okay, QC bar plus QB bar. Okay, here you have QB bar. So if you apply De Morgan's law, what you are getting? QC QB whole bar. QC QB whole bar. Okay, so that means what is the combination logic you need to design? AND gate. You need to design as a NAND gate. You need to design the NAND gate. QC QB whole bar. Okay, so here I am designing. So that means here I am taking JK flip flop. So 3 JK flip flop that is operating in toggle state. So toggle state. So this is JAKA. Okay, JA, KA and QA, JB, KB and QB, JC, KC and QC. Okay, so these are the asynchronous inputs are there. So when these are activated, irrespective of clock and reset, clock and input, it will force the output to 0. Okay. There are one more thing is there, that is preset is there. Preset means this is also one more asynchronous input. So when it is activated, irrespective of input and clock, it will force the output of the flip flop to 1. Okay. So here I am giving this one with what 1 only. Okay, toggle state, and the first flip flop always toggle. Again, QA is acting as a clock for the next flip flop. As I am developing up counter. Okay, and next so QA and QA and QC connected with which gate? NAND gate, and this is given to the clear signal. This is given to the clear signal. Okay. Suppose if you take normal less than that value, suppose 100 if I take, okay, 100 means what? So NAND operation of 0 and 1 is what? 1 only. Okay. So 1 will be coming. So 1 will be coming to the clear means what? So clear is not activated. So normally it will do counting. It will be in the functional mode only. Suppose when it is coming to 110, okay, 110, okay. So 110 or 111 if we take. So 1 and 1. So 1 and 1 means what? The output of NAND gate becomes 0, and so clear signals becomes 0. Okay, irrespective of input and clock, it will force the output to what? 0. It will start from 0. Okay, so this is the basic design of Mod 6 counter. Okay, hope you understood. Any doubts or queries? Shall I move with coding? So this is the design of what? Mod 6 counter. Is it fine? Anyone? Okay. So I will design the Mod 6 counter. So this is the Mod 6 counter. So here you see module mod 6 counter, input clock, input I am declaring external active low reset, external active, that clear reset is there, no, master reset underscore n. Okay, so this is the nomenclature we need to use. This is active low reset means reset underscore n. Okay, external active low reset, output 2 down to 0 q. Okay, I am declaring reg qa qb qc, and wire clear underscore n. This clear underscore n I am declaring with wire data type. Okay, and assign. So that means I need to NAND logic. What is NAND logic? Resets when QC cube equal to 1. That is when it is comes to 110, it should reset. We also include the master reset for initial condition. That means assign clear underscore n is master underscore reset underscore n, and NAND of QC and QB. Okay, you need to combine with this logic, and then you need to give it to the clear underscore n. Okay, and flip flop A, that is always toggles, no, always at the rate negate of clock or negate of clear underscore n begin. So clear underscore n, negate of clear underscore. So when it is going from 0 to 1, so what happens if negate of clear, that is active low clear, no, that's why negate of clear. If not of clear underscore n, okay, not of asynchronous, this is asynchronous reset, that's why I am declaring like this, not of clear underscore n. So clear underscore n equal to, that is 1. Okay, that is not 0. Okay, so you are making that as 0, otherwise uh, qa equal to not of qa. Okay, and flip flop toggles are negative edge of qa, always at the rate negate of qa and negate of clear underscore n begin if not of clear underscore n. So what you need to do? So when clear equal to 0, I need to make that as clear. Okay, otherwise it will be in the functional mode, qb equal to not of qb. Okay, again flip flop c msb toggles are negate of qb, always at the rate negate of qb and negate of clear underscore n begin if not of qn, so not of clear underscore n, if clear underscore n equal to 0, so I need to clear this, okay, clear the output of the flip flop, else it will normally toggle, it will toggle, that means normal operation it will done. And at last assign q equal to, I am using concatenation operation, qc qb and qa and end module, okay. And coming to the test bench, same thing. So we need to declare the internal variables, okay. So what are the internal variables? Clock master underscore reset underscore n with the reg data type and q with y data type. I need to instantiate my design in the test bench with the design name and instance name, and I need to generate the clock as by clock equal to not of clock initial begin, and the clock I am applying 0, and I need to assert the reset. That means when you should asset reset master underscore reset underscore n equal to 0, okay. After 15 time minutes I need to release the reset, okay. So release the reset, I need to run for 150 time minutes. So I need to display in the tcl console and I need to use the dollar monitor, okay. So this is the code. Is this code is fine? Shall I move forward? Yeah. So this is mod 6 counter. So just copy this and just go to the design sources, create the design sources, and choose the location, asynchronous counter, select OK, finish, OK, yes. So asynchronous mod 6 counter. So copy this code and paste here, save, and next coming to the test bench. So this one module name I need to copy, go to the simulation, add simulation sources, create simulation sources, choose the location, asynchronous counter, select OK, finish, OK, yes, and tb mod 6 counter, okay, and select this, copy this, and here paste, save. So my design is instantiated. Right click, set as top module, set as top module, run simulation, run behavioral simulation. Okay. So see in the TCL console, so it will count when reset equal to 0. So that means it will be 0 only. When reset equal to 1, it will go to the functional mode. So that means it will count from 0, 1, 2, 3, 4, 5, and again 4, 5 like that. I'm getting okay. I need to check this code. Once again, I need to check this code. If you see here, so normally if you want to run this code up to here, so it will count from 0, 1, 2, 3, 4, 5. Again it's starting from 4. So it should start from 0. But so normally it is counting as mod 6 counter. Yeah, this I need to check this one. Okay. So this is the mod 6 counter. And next is decade counter. So decade counter is actually like so decade counter means it should count from where, should count to, it should count from 0 to 9, okay, that is decade counter, okay. So how to design decade counter? So you need to develop the logic. So it should count from where, 0 0 0 0 to 1 0 0 1, again it will come to the initial state, okay. So this we call as mod 10 counter only, or we can call as decade counter, okay. So how to design this decade counter? How many flip flops are required? So here 4 flip flops are required. So just four flip flops I am drawing. First you need to design nearest mod of a counter. First I need to design the mod 16 counter. Okay. Let us take this is TA, QA, TB, QB, TC, decade counter, TC, QC, and TD and QD. Okay, so first common clock is applied, direct clock is applied, and this is acting as a clock for the next flip flop. This is acting as a clock for the next flip flop, and all this T inputs should be operated in the toggle mode. Toggle mode. Okay, that is one. This is operated in toggle mode. So when it will come to 1010, okay, 1010. So then uh, it should come to the initial state. Okay, so if you take this one, this is MSB QD, QC, QB, and QA. Okay, so QD QC is there, no? QD QC. So this is QD and QB. Okay, so QB, this is connected to what, NAND gate. Okay, and here you have clear signals. Here you have clear signals. This NAND output is given to this clear signal. Suppose if you take any number less than 9, suppose if I take let us take 7, 0, 1, 1, 1, triple 1. Okay, so that means 1 and 0, your output is what, 1 only. So this 1 is given to all clear signals. Okay, so all clear signals, that means normally it will count. Normally it will count. Okay, 1 1 will be given to all the clear signals. Suppose if you are giving greater than 9, if I giving 1010, so 1010 if I am giving, so that means what happens, 1 1, the input you are getting 1 1, output becomes 0. So that means 0 is coming to all the clear signals, so it will force the output toward 0 only. So it will start from where, 0, and it will count up to 9. After 9, it will come to the initial state. So this is the decade counter. Okay. So decade counter I am designing. So just see here, decade counter. So this is my decade counter. So module decade counter, input clock, input reset underscore n. As I am using 4 flip flops, output 3 down to 0 Q. Okay, I need to declare the internal registers, output of the registers, reg Q0, Q1, Q2, Q3, and wire clear underscore n. Okay, so assign clear underscore n equal to reset underscore n and not of Q3 and Q1. Okay, I need to develop this logic. Okay, and so stage 0, it will always toggle, always at rate negate of clock or negate of clear underscore n begin. If not of clear underscore n, I need to clear this one, else normal operation. Okay, when clear equal to 0 only, then it should reset. Okay, it should reset. And stage 1 toggle for q naught, always at the rate negate of q naught or negate of clear underscore n begin. If not of clear underscore n, q1 will be 0, otherwise q1 equal to not of q1. Stage 2 also, stage 2 toggle for negative edge of q1, always at the rate negative edge of q1 or negative edge of clear underscore n begin. If not of clear underscore n, q2 will be toggle to 0, else q2 will be not of q2. And stage 3 is always at the rate positive negate of q2, it will toggle for q2. Okay, negate of clear underscore n begin. If not of that means clear equal to 0, it will be clear, else q3 equal to not of q3. And you need to map the registers, assign q equal to q3, q2, q1, and q0. Okay, this is my design. And coming to the test bench is same only. 5 steps are there. So you need to declare the internal variables. What are the internal variables? Clock and reset we need to declare with reg data type, and q3 down to 0 q you need to declare with y data type. You need to instantiate your design in the test bench, design name and instance name, connection by name, and always hash y clock equal to not of clock. Again, I am initializing clock equal to 0 and reset underscore n equal to 0. Asset the master reset. After 15 time minutes, I am releasing the reset. I need to see for 250 time minutes. Let us take 250 means 2 cycles I want to check. Okay, 2 cycles means nearly 200 nanoseconds. That's why I'm checking for 250 nanoseconds. Dollar monitor means if I want to see in the TCL console, I can see in the dollar monitor thing I can see. Okay. So this one, if I want to execute, just add the design source, create the design source. What is my design source? Decade counter. Okay. Decade counter, copy, and here paste. Choose the location, asynchronous counter, select OK, finish, OK, yes. So this is my decade counter. Next, so select all, copy, and paste, save. Okay, this is my decade counter. Okay, decade counter, and go to the simulation. Add the simulation sources. Next, create the simulation sources. Testbench file, TB file, copy, and paste over here. Choose the location, asynchronous counter, OK, finish, OK, yes. So TB decade counter. This is TB decade counter. So select all, copy, and here you paste and save. So my decade counter is instantiated. Okay, my design is instantiated under the test bench. Right click, set test of module, run simulation, run behavioral simulation. So you can see in the TCL console also. So it will start from where 0, 1, 2, 3, 4, 5, 6, 7 up to 9. Okay. So it is counting. Okay. But after that I am getting random signal. Randomly it is counting. But it is counting. Okay. You can see in the simulation part also. So 0, 1, 2, 3, 4 up to 9. Okay. After 9 it should come to the initial state. This I will check. So you can see in the binary, this is also binary also. Mm, so fit to page. And just zoom this and move this side. You are getting in the terms of binary. Okay. So this is about the decade counter. Okay.